Everyone, welcome back. So there are quite a few announcements before we begin. So people in the Zoom call, do you hear me? Well, okay. Well, first of all, the second assignment was over yesterday night. Now, I think there are maybe some of you who, by default, assume that the deadline is tonight. But I did mention in the class that I moved the deadline by one night because nobody comes to class if the deadline is on the same day. But I'm not sure if that achieved the purpose looking at the class then. And still, approximately 20% of you have not submitted your assignment. So I assume you're taking one late day to submit it tonight. But 20% of the class is big number. So if you're not submitting the assignment, so let me know if this is because you thought the deadline is tonight, or because you really planned to submit it 1 or 2 days late. The third assignment will be released after the lecture, in a few hours. And again, the deadline will be the day before the lecture. Okay, so not the day of the lecture. So that is about assignments. For A1, I think regrading request period was over. So you'll get the regrades, and that will wind up A1. Now, I received several feedback from a lot of you on how to improve this process. Okay, so we are going to do that for A2. And are there any questions about assignment before I move to the next topic? Okay, I think people are still settling down. Okay, so the next topic is about tutorials. Again, there were very few people attending tutorials, especially the Friday tutorial on scikit-learn. I know that there is going to be clash for some of you because some of your labs are on Friday, some of your labs are on Tuesday or Wednesday. So we try to do tutorial on one of the 2 days, in the lab slot. Even if people who had actual lab slot on Friday attended, we should have more attendance. The attendance was less. It may be because you watched the recordings later, but that is fine. But especially for the previous tutorial on scikit-learn, if you missed it, and if you don't know scikit-learn, you should go watch the recording because the third assignment is going to be based on scikit-learn. Okay, so I think I failed to emphasize this enough last week. So a lot of you missed the tutorial. But this is, well, that should not be an excuse. So, especially the next tutorial is going to be about PyTorch. Now, well, it's not going to be useful for your assignments, but it is going to be useful for your Kaggle competition if you want to use PyTorch in your competition. And in general, it is useful for any machine learning project that you want to do in the future. Okay. Now, this this PyTorch tutorial is going to be done by a research software engineer from Facebook, so who is contributing to the PyTorch package in general. So we are really going to have some experts tutorial on PyTorch. So I encourage you to not miss it. If you have a clash, it's okay, but not all 100 of you can have a clash, right? So we had less than 20 people attending the previous tutorial. So yeah.
Are they available as recording fields also?
Yes, all the recordings are available. The recordings are available, but okay, but if you have time during the tutorial, make use of it by attending it live. Is that clear? And other than that, are there anything else that I'm missing? Oh, about the Kaggle competition. So we will be opening up the Kaggle portal soon, even a week before the start day of the competition, so that you can sign up. Okay, so if you have not found your teammates, you can use Piazza to find teammates. Remember that it has to be a team of 3. So find your teammates, be ready, and whenever the Kaggle competition is open, you all have to sign up and also form the team before the competition begins. Okay, so we don't want you to form teams after the competition begins. So the teams have to be formed before the competition begins, so that we stop registrations and then you start the competition. Okay, so if you don't have your teammates yet, find your teammates through Piazza. And there are a couple of questions in the chat. I'm going to come to that soon. Now, to make things easier, I know a lot of you are taking both my courses and you feel that they are in general heavy. So to make things easier for you, like the third assignment is going to be lighter than the first two assignments, like so that you can focus on the Kaggle competition and also on the other assignments. Okay, so like we will be releasing it in like after the lecture, but it is going to be lighter than the usual assignments. So specifically. There are a couple of questions here. Is there an interactive session plan for remote students to find out team partners? Okay, that is difficult. So I know some of the students are permanently remote. So Piazza is really a good option. Please try to post ads in Piazza. Try to find teammates. Okay, and so one thing that we can do probably is I will try to set up what is it called? Gather Town next week. Okay, so sometime in the evening, like so, or well, most of the remote students are from different countries. Like maybe evening is too late for them. I'm going to set up a couple of Gather Towns next week. I will announce the time and the link for people who have not been in Gather Towns. It's like a virtual world where you can walk around and talk to people. Now, this will work only if more people participate. So if you're looking for teammates, then probably participate and find your teammates. So that's one thing that we can do. But in general, like try to use Piazza. And I also learned that there's a Discord for this course, is it? Or is it for MO or for oral? Is there a Discord channel for this course? Okay, so then this is for this course. Like maybe I'm not in that. So I hope you guys don't discuss solutions there. But make use of the Discord if you want to find teammates. And there is another comment in the chat about KNN taking a lot of time. So several of you had this comment. So, well, if you have a very naive implementation of KNN, it is going to take a lot of time, of course, like because you have a double for loop. You have to do it efficiently, like. But this is a good feedback. Like, so I will try to incorporate it next year. Like, maybe give hints that, like, you should be doing it in an efficient way. So, for example, you have 50,000 examples, right? You can construct one matrix for this 50,000 example, and you can take many batches of test set and do the dot product and compute the distance in just one operation instead of double for loop. Okay, so that is going to make things much faster. Anyways, so I will consider that. Is there anything? I think I discussed about assignments, tutorials, and Kaggle. So, and in general, I think the notes for the next couple of weeks are also up, if you have noticed in the schedule. And there are also self-assessment questions on the top of the schedule page. I'm not sure how many of you are seeing it, but that is going to be extremely helpful for you to prepare for your exam. Okay, so and finally, like a quick note about this week's reading. So this week's reading is a very interesting blog post, a recent blog post, which was just released last week, about the very first machine learning data set, which was developed in 1951 or 50. Okay, so it's a very interesting blog post, which tells you a lot of history about benchmarking in machine learning, train test splits, and like generalization and a lot of things. Okay, so it's supposed to be a fun read. Like it's not very technical. So like this week's reading is really light, and I highly recommend you to do that. Okay, so I think that's a lot of announcements. So now let's get into the lecture. So a quick recap of where we were last week, right? Like so last week we mainly discussed about probabilistic discriminating models, right? So specifically we looked at logistic regression, and we also looked at like another algorithm like Dan gradient descent, which is Newton-Raphson method, right? Like which is a second order optimization method, which is convenient if you have manageable number of parameters and a convex function, right? And after that, we started discussing about discriminant-based classifiers. Right? And specifically, we looked at perceptron. So a quick recap. So perceptron is a separating hyperplane method where the idea is to find a hyperplane which separates the data like from, let's say, two different classes, right? Like let's say I have a bunch of classes. Like let's say I have a bunch of circles and crosses. Now, the idea of perceptron is to find a hyperplane. In this case, it's a line, right? So which separates these two classes, right? Now, the model for perceptron was y of x is equal to some function of w transpose x, where the bias is included in the w transpose x itself. Like you can call it w transpose x plus b or w transpose x plus w0, like, but the bias is included here. And the f function that you see here, right? So f of a is a step function. It is going to be +1 if a is greater than or equal to 0 and -1 if a is less than 0. Let's try. So basically, whenever the class is +1, w transpose x is going to be greater than 0 for class is equal to +1, right? And when class is equal to -1, w transpose x is going to be less than 0, right? So let's just call the class to be y. Is it clear? Okay, I think I was using t for class, so I'll just put it t is equal to. Is it clear? So now I can actually combine these two things, right? Like, and just say for all the data points, I want w transpose x of n, t of n greater than 0. Right? I think we have seen this compact notation several times, like in the last few lectures. So the idea here is whenever t is +1, then w transpose x should be greater than 0. Whenever t is -1, then minus w transpose x is greater than 0 or w transpose x is less than 0, right? So this is one compact equation to represent both, right? Now, once we have this definition, so then we developed the perceptron error criteria, right? So we are essentially redoing perceptron here. So the perceptron error criteria was EP of W is equal to minus summation over n belonging to capital M W transpose x of n T of n, where M is basically a set of all misclassified data points. Right? So this error function is actually very different from typical error functions that we have seen so far, like mean square error or log or cross entropy or NLL, right? Like in this case, usually when I write an error function, like I would say summation n is equal to 1 to capital N. Now, in the case of perceptron, we have 0 error whenever there is a right classification, and we have some positive error only for misclassified data points. So whenever you like summation over all possible misclassified data points, like I want to minimize minus of W transpose X and Tn, which means I'm maximizing W transpose X and Tn, or W transpose X and Tn becomes greater than 0. That's right. So that is my perceptron error criteria, and so here is the perceptron algorithm. So it's a really simple algorithm which you can implement in a few lines of code. So you initialize with some random W. Now you're going to go through all the data points one by one. Okay. So for each data point, if model's prediction is same as the class label, you do nothing. Like you don't change anything. Whenever there is some mistake, then you are up your W. In this case, W is equal to W plus X and T. Okay, so I'm not going to redo the update equation again. Like so, we did that last week. So this is basically simple gradient for this piecewise, like piecewise linear loss function. Is that clear? I think this is where we stopped last week. So I mentioned that this simple perceptron learning algorithm would actually converge in finite number of steps, like if we have a linearly separable problem. Okay, so that is perceptron's convergence theorem. And like we also saw an example last week, so where you have this black arrow pointing towards the red class. Okay, so all the red class should be in the black arrow, and you will consider this particular data point. Okay, you see that it is in the blue region, so it is misclassified. So you do a gradient update, then the line moves a little bit like this, right? And then you consider this data point, which is also a mistake, right? Then you move a little bit further, and finally, like you have all the red points in the direction of W and all the blue points in the other direction. Is that clear? So any questions about perceptron before we start today's lecture? Okay, so today's lecture is going to be about the issues with this very simple algorithm and how to rectify these issues. Okay, now what are the issues with perceptron learning algorithm? So first of all, I told you that there is a theorem which says your algorithm is going to converge in a finite number of steps, right? Now, how many steps is this really, right? Like, so the finite number of steps, okay, can actually be very large. Okay, now, smaller the gap, longer the time to find the hyperplane. Okay, I'll give you an example. Now, let's say I have a bunch of crosses and circles. You have wider gap here, so you can start wherever you want. Like you start like this, you slowly move, move, move. You'll find a line which divides these two things, right? Now, imagine this is another data set, okay, which is like this. Okay, now this data set is still linearly separable, right? I can actually draw a line which separates these two things. However, if I start with something like this, okay, I will be moving this according to the data, like according to the data points. Depending on which data point I took, I'm going to move back and forth, like, and the smaller the gap here, the chance that you will end up with this particular line is going to be small. So it's going to take more time to find this line. Okay, now that is the first issue. Now, the second issue is when the data is linearly separable. Okay, there are many solutions. I'll give you another example. So maybe you can use the same example. Now, in this case, there are many valid lines which separate circles from crosses. Okay, so this is a valid line. 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 This is a valid right. Like so, there are many possible hyperplanes separating these two data points because the data is linearly separable. Okay. Now, which of these lines would perceptron find? Any guess? Yeah.
Find any of those.
It can find any of those, but what determines the solution? Yeah.
How the algorithm travels through the data points.
So how the algorithm travels, right? Like, so for example, I'll use green color now. So for example, let's say I started here, okay? Then I slowly move, and maybe when I reach here, there is no mistake, so I'm done. Okay. Similarly, had I started here, So maybe I'll slowly move, and when I reach this point, then I'm done. Right? Now, this is an issue. Like every time you run this algorithm, it is going to give you different solution. Now, well, why is this an issue, right? So now the question is this, are all these solutions equally good? Any guess? Yeah.
First solution gave the user interest to course.
Okay, so maybe I will highlight what you said by drawing another line. So, for example, if you find a solution like this, do you think this is a good solution? No. Why? Yes, because the goal here is not training error, right? The goal here is generalization. Like now, what if my test data point is here? Okay. Now you are going to classify this as cross, while most probably it's going to be a circle because it is close to the circle, right? So now we are going to talk about this issue in more detail, like soon. But for now, the second issue is there are many solutions. Some of them might have optimal generalization error. Like now it is not clear, like whether Perceptron is going to find that solution. Okay. The third issue is even more severe. So the third issue is when data is not linearly separable. Okay, then perceptron will not converge because the perceptron error is based on misclassified data points, right? The data is not linearly separable. You can never draw a hyperplane or a line, right? That's the definition of non-linearly separable data, right? Like so, when the data is not linearly separable, the algorithm will not converge. Okay. However, the deeper issue here is we don't know whether the algorithm is converging or not. Okay. So if you remember from our last week's discussion, the error is not monotonically decreasing in perceptron. It increases, decreases, increases, decreases because we are doing one example at a time, right? Now, it could be the case that for the last million iterations, like my perceptron is in a cycle or loop because of this nonlinear problem, not linearly separable problem, but I have no way to detect it. Okay, detecting cycles can be hard, especially if your data set size is too huge. Okay, now how do we resolve all these issues? Okay, so that is what we're going to do today. So first, probably, well, there's not a lot that you can do with the first issue. Okay, so if the gap is small, it just means the problem is harder. Okay, so probably we will not talk too much about the first issue, but we will try to solve the second and third issue. Okay, so we will probably do it one at a time. So first, let's focus on the second issue, which is the issue of many solutions and like what is the optimal solution, right? So to do that, we are going to do some modifications to Perceptron, like which would take us to the idea of MaxMargin classifiers. Okay, so, well, the camera is not working. Okay, so while the camera is coming back, so the issue that we want to solve now is even if the data is linearly separable, the solution that Perceptron is going to find depends on the initial line from which it starts, right? So it depends on the initial, so the solution depends on initial W and bias, right? And also the order in which the data is presented. Okay. However, our goal is not training accuracy. Our goal is to find a separating hyperplane which has maximum test accuracy, right? Like generalization. Now, this is where the idea of margin comes into play. Okay, so let's say I have a bunch of circles and crosses. Okay, so if I ask you to draw a line to separate these two classes with the goal in mind that you should have low test error or like better generalization. Okay, now where would you put that line? So let's have some options. So would you consider this line? Do you think this will have better generalization error? Okay, now would you consider this line? No, why?
Because it leans towards
It leans
more towards one of the things.
Yeah. So now how about something like this? Right. So this is probably a safer choice because it's somewhere in between both the classes. So in the future, if you have some circles or crosses, they will be accounted for. Right. Now, this is the intuition. Okay. So our goal is going to be to set up an optimization procedure which will result in finding this particular line. Okay. To do that, we are going to use the idea of margin. Okay. First, let me define margin. Okay. So margin is basically the perpendicular distance between the decision boundary, okay, and the closest of all the data points. Is that clear? So here is a visual picture. So now let's say this is one class, and let's say this is another class data point. Let's say there may be a lot of data points. Okay. Now I draw a line like this. Okay. Now this is my decision boundary. Now the margin is defined as the perpendicular distance from my decision boundary to the closest data point. So what is the closest data point here? Huh? So the one on the top, the green one, right? So now this is my closest data point. So I will be considering a perpendicular line corresponding to this. Okay. Now this distance that you are seeing here is the margin. Is that clear? So it is very important that you understand what is a margin so that we can build on top of it. Is that clear? Okay. In terms of picture, it is simple. Okay. So now we are going to define margin mathematically. Okay. So before that, like what is our goal? Like our goal is to find this line which maximizes the margin as much as possible, right? So for example, like if I want to maximize the margin here, like I could just move it a little bit like this. Now the margin is increasing, right? Then I move it a little bit like this. The margin is increasing, right? Now I move it a little bit like this. Now the margin is not increasing because the closest data point for this line, right, is the red dot, right? So it is not the green dot anymore, right? So now my margin is going to be defined based on this gap, right? So essentially, whenever you want to converge, you will be moving between red and green and find this midpoint which has maximum margins, which means which is equidistant from both sides. Is that clear? Is that clear? Okay. Now let's try to formalize this. Okay. Our goal is to find a decision boundary, okay, that maximizes the margin, right? Now we are going to use some of the geometrical properties of decision surface that we learned a few weeks back, right? So if you remember our discussion on linear decision boundaries, we have a formula for like perpendicular distance of a point from the hyperplane, right? Like so, the perpendicular distance of a point x from a hyperplane defined by y of x is equal to 0, where y of x is some w transpose p of x plus p, like we are assuming that we have some basis function, okay, is given by norm of y of x divided by norm of w. Okay, I think this was the third property, like of out of all the three properties of the decision surface that we have seen so far. Okay, now, so this gives us a formula for the perpendicular distance actually. Okay, now further we are only interested in solutions for which the data points are correctly classified, right? So if you have a solution for which the data point is wrongly classified, then that is not our solution point. So we only care about solutions for which p of n multiplied by y of xn is greater than 0 for all n, right? So I can combine these two things and write an equation for margin. Okay, so the distance of a point x of n to the decision surface is given by t of n y of xn multiplied by norm of w. Is that right? So in the distance, we have absolute value of y of x, but we know that we only care about situations where t of n, y of n is greater than 0, right? So you have t of n, y of n divided by norm of w. Okay, or in other words, t of n, w transpose p x of n plus b divided by norm of w. Is that clear? So now this is a definition for a perpendicular distance. Okay, so now we can define margin. So margin is given by perpendicular distance to the closest point x of n from the data set. Okay, so now I'm going to write my objective function. So my objective function is to find w and b which maximizes the margin. So I'm going to write argmax of w comma b. Now what is the definition of margin? Margin is the minimum distance to the closest data point, right? Like so it's minimize over n, t of n, w transpose p of xn plus b divided by. Is that clear? Now we have formalized our goal here. So what is our goal? Our goal is to find the margin, like the maximal margin, like the margin that separates the classes with maximal distance, right? So we are interested in finding the margin. Okay, for a moment, forget about what is this definition of margin. You have some margin. You are interested in finding w and b which maximizes the margin. Okay, so in outer loop you have a maximization problem. Now in the inner loop, this is the definition of margin. So what is margin? Like you just compute the distance with every data point, which is given by this term, and the minimum of all of those things. So that is my margin. Okay. Now you have this max min problem. Like so, Like you have a max in the outer loop and you have a min in the inner loop. Okay. Now this is a very complex optimization problem to solve. So this is not like our usual objective functions that we have seen so far, where like you can just take a gradient step and like you are in this very nice it's like setup that like you will converge to the optimal solution or near optimal solution, right? Like so this is a very complex optimization problem. Okay, so we cannot directly solve, well, we can directly solve it, but it is complex. So what we are going to do today is like to convert this into an equivalent problem, which is much easier to solve. Is that clear? So any questions so far? Okay, so you have to listen carefully today. Okay, so now we're going to convert this into a simpler, well maybe, okay, maybe I'll first write a little bit extra thing here. So arg max w comma b. So this denominator doesn't depend on n, right? So I can just bring the denominator outside. It becomes 1 over w min n t of n w transpose p of xn. Is that clear? Okay, so now we are going to convert this to a simpler problem. Okay, to do that, we are going to make an observation. Okay, that if I rescale w to some kw and bias to some k bias, okay, this does not change the distance from any point to the decision surface. Okay, so if you do this rescaling, then the distance from a point xn to the decision surface, which is given by t of n y of x of n divided by norm w, is unchanged. So why is that the case? So it is very simple to prove that. So let us just consider this distance t of n y of xn divided by norm w, right? So I'm just going to expand things. So t of n. Now my y of xn is going to be, instead of w, I'm going to have kw. Kw transpose p of xn. Instead of bias, I'm going to have k bias. Okay, divided by k times norm. Okay, now I can just take the k out. So this becomes t of n, k times w transpose p of xn plus bias divided by k times w. So k cancels each other. So you get the same distance back, right? So the distance is not affected if I rescale my w and bias. Okay, I'm going to use this freedom to set my margin. So I'm going to use this freedom and say that for the point that is closest to my decision surface, okay, we're going to say that t of n multiplied by w transpose p of xn plus b, okay, is exactly equal to 1 for the point that is closest to the surface. Is it clear? Now I can find a w and b such that this becomes true. Okay, it's like I can just scale w and b such that this becomes true. Now, in some sense, this is a canonical representation because I am saying that the distance to the closest data point is 1. Now you rescale the distance with other data points. Is it clear? So previously, like we computed the distance with the closest data point, it could be, let's say, 5. Then all the other distances were greater than 5, right? So now I'm saying that I'm going to change my w and b in such a way that the distance to the first closest data point is 1. So for all the other data points, t of n w transpose p of x of n plus b is going to be greater than or equal to 1 for n is equal to 1. Is that clear? Any questions? Okay, so maybe I'll quickly recap this in terms of pictures. Okay, so let's say I have a bunch of, as usual, circles and crosses. Okay, I'll give a little bit more margin. Is that clear? Now, let us say this is my line. Okay, now this is the decision surface that I'm considering. Now, which data point would you use to define the margin? So this is the closest, right? So you're going to consider this red point to be the margin. So to define the margin. So you will consider a perpendicular line, and this is your margin, right? Now, all I'm doing here in this canonical representation is I'm going to say this distance of the margin is going to be 1. Okay, consider this as the unit distance. Now you rescale all the other distances, like so distance to this, distance to this, distance to this, distance to this, right? So you're going to rescale these distances so that like they are all greater than 1. Is that clear? Now it looks like a complex thing to do, but you will see that this is going to help our case very much. Now, once I do this, right? So this equality is satisfied. Okay. Now this is going to be exactly equal to 1 only for data points in the margin, right? So whenever this is equal to 1 for some data points, we are going to say that the constraint is active for those data points. Whenever it is greater than 1, then the constraint is inactive for the data point. Is that clear? Now, I'm going to make a couple of statements. Okay, I want you to think about whether they are true or false. Okay, in the beginning, when I start this optimization process, okay, there is going to be at least one active constraint. Is that true or false? Yeah.
That's true because there's always the closest point.
Yeah. So yes, that's a correct answer. So there is always one closest point, right? Like that's how you define the margin. So when I start the process, in this case, for example, the closest point that I have is this, right? So constraint is active for this data point because for this data point, my distance is equal to 1. And for all the other data points, distance is greater than 1. So they are all inactive, right? Does everyone agree? Now, when this optimization process ends, which means I have found the max margin boundary, then there will be at least 2 active constraints. Is that true? Huh? Yes, right? Like so. Why? Because in this case, okay, I don't want to spoil this picture, but I'll copy it to another page. Okay. Now, well, I think I should just draw it. Okay. Now in this case, let's say I start with something like this. Now there is one closest data point, right? So I have one active constraint. Now I keep moving this, like wiggling around, like in the boundary. So at some point, I'm going to discover this line, which has equal distance to one data point from circle and one data point from cross, right? Now this is the place where I have maximum margin because my margin with respect to both the classes is as best as it can be, right? Yeah, question.
What's it at the beginning? There are 2 points taken. Let's say on the
That's a good question. So now, if there are 2 points that are equidistant and they are both circles, that is totally okay. Like, so for example, I could have another point here, okay, such that that's why I said at least one active constraint. Okay, so there could be 2 data points. Okay, however, if you have 2 data points that are equidistant, one is circle, one is cross, then the problem is already over, right? Like, so you have found this correct line, which is in between the 2 classes, right? So in that case, like the problem is already solved. Is that clear? Yeah.
What if the lines starts at an angle and finds the maximal margin at that angle? Won't necessarily be the biggest margin that can exist.
No, that will not happen because the assumption is you are doing both max and min correctly. So there is only one unique solution and you will find. Okay, so now in this case, like for example, sorry. Right. So in this case, you have 3 constraints active. So this is active, and this is active, right? So however, given that you have one constraint from left and one constraint from the right, you have already achieved the max margin. Is that clear? Now, with this new setup, right? So we are going to write our modified optimization function, okay, problem, which is going to be simpler to solve. Okay, so the problem is argmax of w comma b. Okay, I'm going to throw away the, if you remember, like in the previous optimization function, we had Tn y of xn divided by norm of w, right? So now, as per our definition, whenever the margin, like whenever you have the margin, like for the margin, like Tn y is 1, right? So it's going to be 1 divided by norm of w, okay, subject to a bunch of conditions, subject to T of n w transpose p of x of n plus b is greater than or equal to 1 for n is equal to 1 to n. Is that clear? So now this is actually a simpler problem than the previous problem, which was argmax followed by a minimization inside. Okay, so this is a constraint optimization problem. Like you're doing some argmax with respect to a bunch of linear inequalities. Okay, now I can also write a minimum version of this, right? Like so, arg min, because we always care about minimizing things. Like so, arg min wb 1 over 2 w square. Instead of maximizing 1 over w, I'm minimizing w. Now instead of minimizing w, I could also minimize w square. So it doesn't matter. Subject to T of n w transpose p of x of n plus p is greater than or equal to 1 for n is equal to 1. Is that clear? Okay. So we started with the max margin formulation, like which was argmax followed by minimization, and by making this canonical representation, like where the closest data point has a distance of 1, okay, which is something that we can always make by playing with w and b. We have this simpler constraint optimization problem. Okay, now how to solve this constraint optimization problem to find w and b? So we'll take a break now and do that at 1:45 or 1:46. So we will stop here.